Okay, before we get on to the meat of lesson 48, I'd just like to show you that PhET demonstration again quickly. Here it is. I'll try to make this quick. We're going to send a pulse over to a fixed end, and we're going to do it in slow motion. Here we go. So watch this. So I'm sending a pulse over, and when the pulse reflects, it's upside down. And the question is, why is it upside down? And it's a basic application of Newton's third law. The particles, as you can see, okay, let's wait till it comes back to this one right here, even though it's inverting on both. So the particles are going up and down, and they're going to pull up on this clamp here. But since this clamp is fixed in place, so they pull up on it, it pushes down on them with an equal opposite force. So that's why it inverts. In the same way that when you're jumping, what do? You press down on the earth, and the earth has much more mass than you, so it presses up on you and you jump, right? The reason you jump is because you're pressing into the earth and it pushes you up. Newton's third law, equal and opposite reactions. And then if I change this to a loose end, look what happens. All of a sudden, since it's free to move, then the wave does not invert. And it inverts at this end because this is a fixed end. And now, because this is free to move, when it pulls down on this, because it can move, it does move down. And when it doesn't, therefore, it doesn't invert. Okay, we'll stop that and get back to the lesson, which is wave velocity and boundaries. So waves obviously have a speed. They have a speed and an amplitude. Amplitude is the size of the wave. Speed is obviously the speed of the wave. And his basic wave velocity is based on your favorite formula and mine. Velocity equals distance over time. But now we're going to change the distance. The distance is going to essentially be the wavelength. And you've got to be careful with that wavelength, because if you're just sending a pulse, so I'm just as I did in that PhET demonstration, if I'm sending a pulse over there, then the wavelength is that right there. It's the length of the pulse. However, if you're sending a wave that then reflects, and we'll talk more about this when we do superpositioning, then the wavelength is this. So if you've got a sine wave, that's the wavelength. But if you're just sending a pulse, then it's just the length of the pulse. It is not one up and then one down. So we'll talk more about that later. But if it's a pulse, just know that wavelength is the length from the start of the pulse to the end of the pulse. So we're going to replace the D with L, wavelength. And T we're going to place with big T, the period, or the frequency. Now, here's what's going to happen here. Actually, let's do this example first, and then we'll get to the universal wave equation. So this says it takes you 0.54 seconds to flick your wrist up and down while holding a garden hose. If the pulse you created has a length of 0.57, determine the velocity of the pulse. Pretty straightforward. The velocity equals the length of the pulse divided by the time it took for you to create that pulse, which is that divided by that, and you get 1.4 meters per second. Okay. More often than not, though, you're going to get this form of velocity for waves, and that is the universal wave equation. So first, we have to remember that little t is time, but big T is a special sort of time. It's period, how long it takes to create a wave, or how long it takes to do a cycle of something. And that frequency is the inverse of period. So remember that period is seconds per cycle. How many seconds does it take to do one cycle? And frequency is cycles per second. How many cycles is it doing 1 second? So they're inverses of one another. And again, if we take that formula, this is called the universal wave equation. If we take this formula here, though, and we replace D with lambda, wavelength, and then we replace T with big T, and then we substitute in we substitute the 1 over f, lambda divided by 1 over f equals this. And this is called the universal wave equation. Why? Because it works for all waves in the universe. And it's the most important one of this unit by far. A wave in a hot tub is measured to have a frequency of 6 hertz, so 6 cycles per second. If its wavelength is 24 centimeters, determine how fast it's moving. And with the universal wave equation, that's a really easy question because you have the frequency, you have the wavelength, multiply those two numbers, and you get 1.4 meters per second. Example number 3 says the speed of light is 3 times 10 to the 8th meters per second. Determine the frequency of red light, which has a wavelength of 700 nanometers. So in this one, you're given the velocity, you're given the wavelength, and 700 nanometers, you're going to use this a great deal in physics 30, is just 700 times 10 to the negative 9. So you could change that to 7.00 times 10 to the negative 7, but if it says nanometers, the easiest way to express it is just take the number and put times 10 to the negative 9 at the end, and we want the frequency. Frequency equals the velocity divided by the wavelength. And you end up getting this incredible answer. (4.29 times 10 to the 14th hertz. So that is actually the frequency of red light. And just try to imagine that number for a second. That is that many cycles. 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That number is 429 trillion cycles in 1 second. So that's how fast red light vibrates. Okay, we're going to stop there. Waves at boundaries, actually, where we are not doing. So that's it for this lesson. The universal wave equation. Very, very, very important for physics 20 and for physics 30.